Welcome everyone to the San Diego chapter of Papers We Love. This is the July meetup, and the paper being presented this evening is GloVe, Global Vectors for Word Representations by Jeffrey Pennington, Richard Socher, and Christopher D. Manning. Our presenter this evening is Michael Jalkio of Classy. Let's have a warm welcome for Michael.
Cool, thank you very much. All right, so today we're going to talk about, this is the outline of the talk. We're going to talk very briefly about what is NLP, some early influences that contributed to this paper, looking at vector space models. Then we're going to talk about the what and why of word embeddings, talk a little bit about word to vec, and finally we're going to come to the actual paper for today, GloVe. So natural language processing, just by a show of hands, who has heard of it? Okay, good. So as you hopefully already know, natural language processing encompasses a lot of different problem areas, things such as sentence parsing, machine translation, natural language generation, question answering, sentiment analysis, and so much more. Yeah, so it's a pretty big area, pretty actively being worked on, I would say, in both academia and in industry. And there are a lot of hard problems in natural language because we talk very strangely as people, and computers are not that into it. Yeah. So one of the first things that you have to figure out when you're trying to process language is how do you represent it? So this is where we're talking about vector space models. I think a lot of it came from information retrieval. So information retrieval, you can think early Google. You have a collection of documents. Let's get to this. Yeah, so the setup in information retrieval typically is you start with what they call a corpus of documents. That's just a collection of documents. In this case, I've written that our corpus C has 3 documents in it, D1, D2, D3. You typically scan through that corpus and you define your vocabulary up front. So all of the words that exist in your corpus, you would enumerate them. So here we're saying that there are 5 words in the corpus, which makes up our vocabulary. And then typically you would represent documents as vectors of term weights. So here we have our 3 documents again. Each one of the vectors, which represents a single document, is the length of the number of words in the vocabulary. So here, for example, this W11 would represent the count or the weight for term 1 in document 1. Second thing would be the weight of term 2 in document 1, etc. I also want to note that although we are thinking of them as vectors, they are not typically represented as full vectors on your computer, because these documents are typically, your vocabulary is typically very large and your vector is typically very sparse. Each document only has some words, not all of the words that exist. Yeah. So in information retrieval, you then create a query. So this is, your search term that you're typing into Google. And a query is represented in the same way as a document. So it's also a vector of term weights. And then one way to decide which document to return when someone makes a query is to use the cosine similarity. So this, I think, is the most popular, most commonly seen similarity metric, but it's just a way to compare 2 vectors to each other. So you take your query vector, and then you calculate the cosine similarity between it and every document, and whichever one returns the highest similarity is, the most appropriate document to return. And because the vectors that we deal with are typically non-negative with these term weights are only positive, the cosine similarity will range between 0 and 1. Any questions on this? The setup? Great. So then you have to decide, all right, how do we figure out what these term weights should be? What makes sense? And the first approach is to use what is called a bag of words method. So in the bag of words, you look at each document and you just count how many times each word appears, and that is the weight that you're going to use in your vector. So here I have 4 documents now, and the vocabulary is of 5 words. So the words are the, dog, runs, horse, and eats. And you can see how the documents would be represented. And yeah, I made the dog eat a dog because I wanted at least one of the sentence to have more than one word. Hopefully that would not happen in real life. Yeah.
Naive.
All right, so there are some problems with the bag of words approach. I think the biggest issue is that bag of words overemphasizes common words. So here, in our very, very small data set, we see that every single document contains the word the. And because of that, you're going to say, oh, these documents, have some base level of similarity to each other because of that word the. It turns out that in real text, all documents contain the a lot. They also contain lots of other words like and so yeah. So this is bad in the bag of words model. That's essentially noise that you don't want to deal with. So an improvement is a model called term frequency inverse document frequency. And those are essentially 2 different metrics that you would calculate and then multiply together to generate your weight. So here, we're taking kind of the most basic term frequency, which is just the count of the words. So you're taking the bag of words model, and that would be your term frequency. And then the inverse document frequency, in this case, it's that term on the right. So it's the log of the number of documents on the top, and on the bottom, it's the count of documents that have the given term in it. So that right metric, the inverse document frequency, for a given term is kind of like a global statistic. It doesn't depend on which document you're looking at. That number would always be the same. So at the bottom, I've gone through and I calculated the inverse documents frequencies for this very, very small example that we have. And you see that actually in the example that because it appears in every document, the inverse document frequency would be 0. So we would actually completely wind up ignoring that word when we're weighting documents. Then you see that the words that were less common wind up having a higher weight. And the idea in this model is essentially that words that appear very rarely, if they appear in 2 documents, it's probably a very strong signal that these documents are related to each other. Whereas words that appear in everything, probably not a great signal. Yeah, and in these vector space models, there are many, many different ways to define both term frequency and inverse document frequency. And it depends a lot on what your application is trying to do, how you pick and choose which ones to use. Cool. Any questions on this before we move on?
Only slide 1.
Yeah.
The very common words, how about using them for error correction? I mean, I know from my experience as a simultaneous interpreter, if you don't hear a certain very common word, it's very probable that that there's some error in the rest of it.
Mm-hmm.
Is there any way for this calculation to use very common words or to have some error correction?
Anything's possible. Armin, did you have something?
Yeah, I can speak to that a little bit. I used to work on the TF-IDF search engine, so so I can say that it's a lossy model, and so you're basically there are techniques for dealing with things like the word the. One of them is to actually eliminate eliminate a set of stop words from the entire index. That also yields an efficiency because the thing is where the rubber hits the road in trying to implement these things is actually common terms. The cost of each query scales for the most common terms in the query, although those are the ones that are least useful in discriminating. So you can see that this is a very it's not a great model. I mean, it's better than a lot of things, but it has a lot of failure modes. Another way that it fails is if you take out those stop words, you can't do, if you eliminate from the index, you can't do phrase matching.
Okay.
So there's a lot of reasons to preserve, well, there's a lot of trade-offs there is what I'm saying. So you're not wrong that absolutely that would be an advantage to be able to detect that thing, but it's sort of outside the scope of TF-IDF. Does that make sense?
It does, yeah. Because, for example, I don't know if you study Latin languages, when you study something, so dog, English, for example, in Italian or French, le chien, il cane, you always put an article before it, just in case the string has a verb form, which is totally different.
Right.
So you got Bayes' theorem. I mean, if you want to go through every document.
Yeah, well, yeah, but it also depends on how powerful your computation is. I mean, I like to, since I have no skin in the game as far as cost of anything, I always think, let's say everything's a quantum computer, you know?
Maybe that sounds like something we should say from the end, though.
Yeah.
Agreed. Good stuff, though.
Yeah. All right, cool. So that's kind of how we represent documents. So the next question we come to is, how do we start to represent individual words? So here, similar to the bag of words model for documents, one, probably the most naive approach to represent an individual word is to use what is called a one-hot encoding. So in a one-hot encoding, essentially you're going to give each word some integer identifier. And again, you have a preset vocabulary, right? So there's a certain size of your vocabulary. You're going to only be able to represent, say, 10,000 words. And then each of those 10,000 words gets an ID. And then how you represent them, again, abstractly tends to be as a vector with 9,999 zeros and a single one. And yeah, that's it. That's the one-hot encoding. So obviously there are a lot of downsides to this way of representing words, like pretty much only downsides, because every word is identical in the sense that they are all orthogonal to each other. You're not getting any information about which words are related to each other. Yeah, there's just none of that at all, but you are able to represent words, so that's a plus. So the idea of word embeddings is essentially that you want to take these one-hot encodings, instead of using them, you want to have a featurized representation of each word. So here's kind of an abstract idea of, right, so before we're going from these one-hot encodings, these 10,000 length vectors, one in them, and we're going to embed this down into a lower dimensionality space. So that, for example, here we have 3 features: gender, royal, and food. You can see man and women, have opposite signs on this gender feature. King and queen have like negative and positive, very similar to man and woman. The food feature is only shared by apple and orange. So that's the idea when we're going to start looking at word embeddings, is how do we figure out a good way to generate these featurized representations for individual words. The only other thing to keep in mind is that when you're actually generating these word embeddings, they're not going to be that your feature is, oh, okay, this is the gender feature, this is the food feature, this is obvious to me, it's like a 1 or a 0 or whatever like that. You're going to generate just a set of features that maybe make sense to your algorithm, make sense to your computer, but tend to be pretty, black boxy.
This is why the orange is slightly female.
Yeah.
I was trying to figure that out. I'm like, why is it? Never mind.
Yeah. I do think this was I took this from like an Andrew Ng course. I do think it's weird that he like pretended that the features could be perfect, but then didn't pretend that the weights would be perfect. Right?
In practice, like, are you ever able to kind of figure out what a feature is? Like, are you is the feature interpretable in some way where like you kind of do some thinking, you're like, oh, this is this concept. Maybe it's not a single word.
So what's very common is to take these embeddings and project them into a lower dimensionality space, and then to do some sort of clustering. And then people will, afterwards say, oh, hey, like if I kind of squint, this cluster is the blah 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 cluster, and like, oh, this cluster over here is like, yeah, and we'll see some of that a little bit later on. Yeah, sweet. All right. So the next question is, yeah, why do we care about these word embeddings? Why do we want to generate them? What are they any good for? So the example, again from Andrew Ng, is one potential thing we could do is it could help in a named entity recognition task. So this is another NLP task where essentially you want to take a sentence and you want to say what in the sentence are named entities. So the example here is maybe your training set has the sentence, Sally Johnson is an orange farmer. What you would want is your algorithm, well in this case it's the training set, so what you would have labeled for you already is the fact that Sally Johnson is a named entity, and nothing else in there is a named entity. And then maybe your test set contains, this is unlabeled, so you want your algorithm to be able to figure out in the sentence, Robert Lynn is a durian cultivator, what the named entity is in that sentence. So the point he made was that chances are, for most people, your text data did not contain a lot of durians. It also probably did not refer to farmers as cultivators. So you're dealing with a small data set where you haven't been able, your algorithm hasn't been able to learn all these generalizations. But if you had, say, word embeddings, what you could do is you could say, oh, okay, durian is a fruit similar to orange, and a cultivator is some sort of thing that's similar to a farmer. Okay, well, this sentence looks very, very similar to this previous sentence that I've learned about before, and you can hopefully successfully identify that Robert Lynn is a named entity.
It's sort of an odd example because he's picked for his training set. I mean, orange can be orange the fruit, orange can be orange the color.
Yeah.
And you could have some other words in there that could be it could be more ambiguous.
That is funny. Yeah, I just noticed that.
I was kind of wondering, why didn't he pick something that would be much more unambiguous in the training set?
Like a purple farmer.
Yeah.
Or apple, because apple's not a color. It can't be a color or anything else as far as I know.
That's true. And
Recruiter.
so this is also a major shortcoming of word embeddings generally, where when you are learning word embeddings, you're figuring out a single way to represent a word. And again, we know from our use of language that words can have very different meanings in different contexts. This is just like, yeah, this is an issue with the entire approach. Cool. So what we were able to do there when we're comparing, durian to orange is we're essentially using this idea of nearest neighbors as synonyms. So words that exist at a similar place in this vector space, chances are that they are very, very related. So this is an example from the GloVe website where they're showing the nearest neighbors to the word frog. You see some interesting things. You learn that frog and frogs are close, which is actually sometimes difficult for like a natural language system to figure out. Toads and yeah, a bunch of other things that I don't know how to pronounce or really what they are, but there are pictures. Yeah, so that's a cute Rana right there. Yep. Yeah. So more generally, what we're doing here is called transfer learning. So we're applying what we've learned from word embeddings, and we're trying to transfer it to this named entity recognition task. And the advantage of this is that you can pre-train word embeddings on a large corpus of data, and it's an unsupervised learning approach. So you don't have to go through, you don't have to label your data. Your algorithm's just going to eat it up, chug away, produce some word embeddings, and then you can use them for many different tasks after that. Or in some cases, you can just use someone else's pre-trained models. So it's very common, both Google with Word2Vec and the GloVe crew from Stanford. They've released several pre-trained models on different corpi. And yeah, you can, yeah, I don't know if that's a word. Corpuses, yeah. So you can use these on your problems. Yeah. Any questions on this here? Corpuses?
I'm looking it up.
We'll have a definitive answer shortly.
Live fact check.
Oof.
Or check. All right.
Yeah.
It's true, it's in the internet.
I think another Yeah.
Corpora.
Oh!
That's right.
Wow. Corpora, there we go.
wow, I was way off.
Just say corpuses, people know what you mean.
More likely. So another thing to consider with these is, for example, Word2Vec is a model that came out of Google. So right at Google, with their modern systems, they're throwing a bunch of different signals into a big soup of, search, and they're just trying to squeeze out whatever meaning they can from that. So this is a thing here where, they don't have to really rely too much on the word embeddings being perfect, because it's just one signal to add to, oh, okay, now I know that these words are related to these other words, and maybe that'll help. Cool. So the other thing that you see come up a lot in word embeddings literature is people really like analogy tasks. So you'll see something like woman is to man, as queen is to blank. So we've gone back now to our simple word embeddings example. And the way that you could answer this question is the analogy that you subtract the two vectors for those words. So here, woman minus man is approximately that vector. And then what you do is you say queen minus, and you do every other word. And whichever vector comes out the most similar to the woman minus man vector answers the analogy. And yeah, this is like the de facto example that is used, but there are many others. So here, for example, is again from the GloVe website. So this is showing that same woman-man relationship. So you see that it learns, heir and heiress, uncle and aunt, and the vector differences between those points look kind of the same. And again, this is, in this image, they're taking what are 300-dimensional vectors and projecting them down on a 2-dimensional space so that we can understand it. Yeah, it's not the case that it looks exactly like this in reality.
So could we then look at a group of, drop a whole corpus on that that graph there, and could we say if it looks like we're going up about that distance, roughly straight up and maybe a little to the right, that's likely to be a gender relationship?
No, because they're only plotting the pairs of words that are gendered, they're able to say that here. But because you're taking, again, like a 300-dimensional vector and reducing it a lot to fall into this space, it wouldn't, there would be lots of other dots that follow that relationship that just in the 300-dimensional space we can't picture have a very different relationship.
I don't know what how to ask this question, but I guess it's you're using the term vector here a lot, like a programmer would be familiar with, but then analogously, the point and magnitude version as well.
Yeah.
And I guess my question is, you mentioned cosine before, and I could see perhaps how it would be possible to get the cosine of a number of vectors that were. How is it that these values, that are essentially just dummy values that are dimensionless, meaningless values, you can perform useful arithmetic on them? Well, like earlier, before you had extracted the gender component of the word vector. How is that extraction process occurring, and why is it most natural to represent words as n-dimensional vectors?
Yeah. So first, the gender part is you would not actually, you wouldn't be able to pull out a feature that represents gender in a real system. And then the reason that these analogies exist and the fact that the vectors have these nice properties is because the systems and the algorithms that they're using are designed to, poop out those properties at the end. Yeah, so it's designed to do that. It's not that, well, in the Word2Vec case, it is kind of coincidental that it turned out like that it worked out so well. but GloVe is very much designed with, okay, we want these nice properties to come out at the end. Let's put these constraints in place and now find some embeddings.
Okay. The optimization is such that, or the loss function is such that you're penalized for having bad analogy values.
Right. Yeah, yeah. Cool. Yeah. Cool. So some other analogies that they have as examples, again from GloVe, is here they're able to show that there's a similar relationship between companies and their CEOs. It's also able to learn relationship between zip codes and the cities that they are in. And here it's able to learn the relationship between a word, its comparative, and its superlative. Yeah, so pretty cool. Does a lot of crazy stuff. Vectors. All right. So next up, I'm going to talk briefly about word2vec. So again, this is kind of the model that popularized word embeddings. This came from Google. And word2vec comes in two flavors. So the first is called the continuous bag of words model, often abbreviated as CBO. I don't know if that's how they say it. And the task that they're trying to do there is, given a context, try to predict the word that fits into that context. So as an example, the sentence, the quick brown fox jumps over the lazy dog. And so you choose how to define your context. So here I'm taking the example of a context which is 2 words prior and 2 words following. So some example things that you would want your algorithm to learn is to try to fill in the blank for the quick blank, fox jumps, quick brown blank, jumps over, and brown fox blank over the. So this is the task for this machine learning problem, and they're going to train a system that is able to do those predictions well. Okay, then the other one, I personally think it's a little bit stranger in the way that it's trained, at least, is called the skipgram model. So that they're just taking it and they're flipping the problem. So now the task is, given a word, basically give me one of the words that exist in its context. So now if your input was brown, valid responses would be the, quick, fox, or jump. For fox, it could be quick, brown, jumps, or over. And for jumps, brown, fox, over, or the would all be good responses. And I think the other interesting thing in the skipgram model is kind of how it's trained. So it's trained by giving the algorithm just pairs of, here is one word, and here is like one potential correct context. And essentially they weight it so that for fox, for example, typically when they train these, they would want brown and jumps to appear more often as training examples than the words that are further away in the context.
Is there a reason that their window is 2 words on either side as opposed to some other number?
So this is my window. Yeah, in practice, I think like they normally use 10. But I'm not sure on that. Don't quote me. Camera. All right. Cool. So the way that they build a system to succeed on these tasks is with a neural net. I would not call this a deep neural net. It just has 2 layers. So the way that this works is, as input to the problem, you get the thing that we're all very familiar with now, a one-hot encoding. So again, you picture this as a vector with a bunch of zeros, and then 1, 1. Oh, this is also the skipgram model. So the input is 1 word, and then on the other side, the output is, again, from neural nets, softmax classifier. So essentially what that output layer is going to do is give a probability for every word in the vocabulary that this is, one of the context words. And then typically what you would do to actually, decide if the algorithm be good or bad, is you would choose whichever word has the highest probability as the one that you try to return. Yeah, and then on the middle part is what is called a hidden layer. It's not hidden because you can't see it or anything like that, or it's mysterious. It's just not the input or the output layer, so that's what they call it. And the hidden layer you can basically think of as a matrix. So it winds up being a 10,000 by 300 matrix, where 300 is the number of features that you're trying to learn. So basically you're going to take this input, multiply it by this matrix, and then run this softmax and output some probabilities. And you're going to do this many, many times. You're going to backprop and all this neural net fun stuff. And at the end, you're going to have some word embeddings. But what's interesting, I think, about Word2Vec is that you're not getting your word embeddings from the output. And you've been training on this problem of predicting context words from random words. But then you're saying, okay, great job, algorithm. You got really good at this problem. I'm going to ignore your output from now on, and I'm going to take out your insides. And like, these are my word embeddings. This is what I was really interested in. So yeah, what you wind up having is this matrix, which is a lookup table for your word embeddings. So again, in this example where there's 10,000 words in your vocabulary and 300 features, you just have a row for each embedding. Cool. Questions about Word2Vec that are hopefully not deep? Light questions. It's very clear to everyone. Awesome. Wow.
Clear enough for now.
Yeah.
Would you call this an autoencoder? Like,
Yeah.
because like the output layer, it's not the same. It's not quite the same as like you're trying to predict the out. Like you're trying to just get the same layer back.
But yeah, it's not an autoencoder. But yeah, the ideas are very similar. Yeah, so you're taking this thing, squishing it down to lower dimensions, and then popping it back out on the other side. Definitely. Cool. All right. So this is where GloVe comes in. So GloVe, the authors of this paper, I think, they look at Word2Vec, they're like, okay, this is pretty good, comes up with some nice word embeddings, but we have some issues, not a big fan. So I think they come in with my read of it with two main goals. One is to be more computationally efficient. So it turns out that doing this softmax classification is like pretty computationally difficult, training this model. So they say, okay, it's kind of weird that you're training this model to do this thing that you're not actually interested in. Hopefully we can create something more computationally efficient. And then I think they want to have a clearer training objective and motivation. All right. So the paper starts off and it defines some things. So these are some statistics that you can calculate about your corpus. So they define xij as the number of times that word j occurs in the context of word I. Most of the time, xij and xji are the same, but that's not always the case. You can define a context that, say, like only looks forward. So one word is in the context of it's not symmetric. Then they define an xi. So this is the number of times any word appears in the context of word I. And then they define pij, sometimes written as p of j given I, which is the probability that the word j appear in the context of word I.
Can you ever define precisely what they mean by in the context of?
So for what they train, I think it's similar with I think they use 10 words. Yeah. Still don't quote me on that. But yeah. But so they also say in the paper that they tested using an asymmetric context, which I was very confused by. But
Does that mean maybe the window's not the same on both sides?
yeah, so yeah, it's typically that right. A lot of the cases you learn something about a word by the words that preceded it, or well, I guess it works in both ways. But
When you say 10 words, 10 in both directions or 5 in both directions?
I think 10 in both directions, but not sure.
That could be kind of interesting, actually. The be asymmetric.
I mean,
You could learn some interesting
Yeah.
things from the patterns.
As far as context, is there any kind of recursion? I mean, in context, once you find a context, and then find a context of a context.
Oh, no. So this is very like these are just statistics about which words appear near each other. Yeah, they're not trying to do anything really intelligent here. And actually, I think that's like a big point of theirs is that with just these statistics, like that they can learn a lot just based on the basic statistics of the corpus, and that they don't have to do anything crazy. Cool. So the next thing they do in the paper is they look at these co-occurrence probabilities. The example that they give is with ice and steam. So if you're curious for, say, two words, ice and steam, and you want to see how these words are related to each other, the idea that they present is to probe with some other words. So here they have solid, gas, water, and fashion. And what they say is kind of the most interesting is you want to look at the ratio of these words given the other words. And yeah, so what they say is that for words that are related to I but not to J, that ratio will be a large value. So here, for example, you can see that solid comes out to be a large value, 8.9, because it's related to ice but not to steam. Then you see for words K related to J but not I, the ratio will be small. So gas is related to steam but not to ice, small value. And then for words that are either equally related to both words or related to neither word, the value will be close to 1. And their point is that these ratios of values are actually what we're most interested in, that tell you the most, not the probabilities themselves.
I think for many people, ice and steam are very, very close conceptually. Here instead, they seem to be far.
You couldn't infer that from the context of this table.
Yeah.
All right.
You know, it just seems that, I mean, the common.
Well, yeah, so ice and steam are
But this is
Yeah.
Yeah.
Solid given ice, solid
Okay, yeah.
given steam, gas given steam.
Okay, so it's like a graph, a directed graph.
Yeah, I mean, there's like a ton of, you're going to have these relationships between, any given pair of three words. So it's kind of to conceptualize hard.
This is going to be
And these are
impacted
for
by the
corporeal
corpus too, because I mean, if they pick a bunch of papers that are all from a certain area of the scientific literature, then that's going to be very different than if they pick, documents from the popular literature.
Yeah.
Wikipedia 2014 was one of their.
Yeah, so they train on a few different data sets. And yeah, I don't think they described which set this was, but this was based on a real corpus of data, like these numbers. But that's not to say that these would be the only possible numbers that would make sense for this collection of words. All right, so the next thing is they go through and they design their model. So I think this is really, this is the meat of it. This is the GloVe algorithm. And this is also why I like this paper. I think that they present kind of the rationale of how they build up this model in a very logical way. Instead of just many papers, they just, oh, here's our end result and it works and like this is awesome. Yeah. All right. So what they're trying to do is they want to figure out a function f that's going to take in 3 vectors, 2 of them being the words that you're interested in, and 1 being this context word, this probe word from earlier. And then you want this function to return something that is approximately this ratio of probabilities that you've calculated already. All right, so the ratio of probabilities, this is not something that you need to learn. This is going to be calculated directly from your corpus. You have these word vectors and the context word vector. They describe in the paper that those should really be interchangeable. In the case, like, it doesn't matter which one you call the context and which one is the word. You say potato, I say potato. Yeah. And then, what they're curious is figuring out what is this function that I can learn that's going to tie everything together. Well, no. So you're not going to learn the function. What is the function I can define that's going to enable me to learn these guys. Right, so you know the thing on the right, you want to learn word vectors, which are going to be your embeddings, and you want to relate those two sides with some function. Yeah. All right. So the first thing they say in the paper is they want the relationships between the words to be embedded in a vector space. So the way they do that is they're just saying, okay, essentially, yeah, I got this here. Right, I want to encode a relationship between word I and word J on the left, because there's this relationship between word I and J that's represented by this ratio on the right. That's the first thing they do. They go from, okay, instead of taking 3 inputs to my function, probably I'm going to want to take 2 inputs. All right. The next thing they say is, oh, we want to work in these like simple linear structures. So they're kind of complaining about the fact that on the left side, they've got this function that takes in 2 vectors. And on the right side, you take in a scalar value. Like, nah, we're not a big fan of this. Like their approach that they say would be, typically you throw a neural net at a problem like that. They don't want to do that. So what they do is they take the dot product of these 2 vectors. So now on the left, you have some function f that's going to take in 1 scalar value, and we're going to try to, on the right, it's also a scalar value. Scalar. Cool. All right. Now the next, yeah.
Sorry. I was going to, isn't the dot product of a vector and a vector also a vector?
Yeah. No.
It's sometimes called scalar product.
I thought multiplying a vector times a vector.
This is the one where you take the products of all the elements and then add them all up. Yeah. Dot product. Cool. So the next part is where the paper honestly kind of loses me. We're going to try to bumble our way through it a little bit. So next they say, well, really a word and a context word should be an arbitrary decision, like which you call which should not matter. And I think they say that for this to be possible, the co-occurrence matrix, it needs to be symmetric. This is the part where they lose me, because later they say they train on a non-symmetric context, asymmetric context. I don't get how they do that, but yeah. So these 2 points.
Well, they're just saying that then if they train in an asymmetric context, then that property would not hold. If they train in an asymmetric context, then you won't get a situation where the word and the context word are interchangeable.
Yeah.
It's only possible when they actually do have the symmetric matrix that they're interchangeable.
Yeah.
Why?
Because in the asymmetric context, let's see, what's the easiest way to put this? If you add the I given j will be the exact same as j given I if you're looking 10 words in advance and 10 words behind. But if you're only looking 10 words in advance, then it's going to give you a different number for which one you use as the context variable. Because say you add some word like Indianapolis 500. 500 always appears after Indianapolis. So in fact, if you use 500 as the context word, it won't even know about Indianapolis at all.
It had no look at. You're just saying where it only looks one previously and it has no context for the future, or
right. But if they are symmetric, and that's represented by an invertible matrix or a symmetric matrix, then you are going to be able to switch them up. But if they're not, then you won't get that.
Yeah, I get what you're saying, but I mean, it seems to me like you wouldn't it just change the probability? I guess I need to ask more questions to you about this.
I don't know. I'm kind of bullshitting here because I mean the thing is that I mean I understand the symmetric matrix aspect of this, but I don't really understand what it means to do the switch up of the context the context word and the other word. That seems wrong to me.
Why don't we take that offline as a contemplation?
Fair.
All right. So I think what they're trying to say is right now, essentially, you couldn't define the function and, just swapping which one is the context and which is normal, they would not be the same necessarily. So now they want to enforce that on the function, that they can do this. So this is where they really lose me. So they want to now say that they want the function f to be a homomorphism between the groups the reals and addition, and the reals greater than 0 and multiplication. So I tried to look up what this meant. I think this means that f is a function that maps from the reals to the reals greater than 0, which that part makes sense to me because it's returning probability ratios. It's going to be greater than 0 and take in a real value. Like, that makes sense. And then this was the definition I saw that was like what a homomorphism is. This f of a plus b equals f of a times f of b. It was very unclear to me how this statement mapped, like if this holds, this holds. If anyone knows about that, it's awesome.
Isn't that just transitivity?
Right. But it was just like, I couldn't tell here.
Well, just look at the division as inverse multiplication, right? Then on the left, you're distributing your function.
You have to distribute the multiplication.
Oh, okay,
and transpose
Yeah,
first.
distribute the multiplication or the dot product, and then after that.
Can you do that though? I don't.
Yeah.
Okay,
Yeah,
that's valid.
Transpose is linear. Multiplication is linear across subtraction. So you get wi transpose w tilde minus wj transpose w tilde. That's a difference. Homomorphisms with differences will be the same. Like,
That also
both
confused me.
minuses. Yeah.
Yeah.
So yeah, it's.
I didn't know
possible to
when
write
you
it
were
down.
allowed to take. Yeah.
Yeah.
I get how they're.
If addition goes to multiplication, then subtraction goes to division.
That's what I thought.
Yeah.
Okay.
It's like one line that I could write.
Sweet. All right. So it all works out. So next they want this f to obey this property. But they're still. I'm personally struggling a little bit. So they throw a lot of these things up there, and by this equation and that equation, yada yada yada. So what I have here is right. Now we've said we want f to equal that guy in the middle, and we've already said that f is going to equal that guy on the far right. So then they're saying, all right, if we define the f to basically be the top of that fraction over there, and those things kind of map to each other pretty well. And then if we say, okay, now f is the exponential function, then also this other part winds up working out with that relationship of the triangle. Does that make sense? Maybe. Good enough.
But it's good enough.
All right. So now we've kind of moved into a very, very different looking function, which we're going to try to learn. So this exponential function of that guy in the middle needs to be equal to, and that's right. That was our definition of pik. This xik over xi. So you can take the log of that, and now our function winds up looking like this. All right. So then the next part that they have an issue with, they're like, okay, at this point, I can almost swap these two things, the context and the word itself, and it would be okay. The only issue is that we have this log of xi, which still does not work out. But they just take like a common machine learning approach to this, and they say, all right, that xi is unrelated to the k, so we're just gonna squish it into a bias term, which is just like, oh, we'll just, yeah, whatever, it doesn't work out, we'll stick it in there, and it's okay. And then, again, so that we still have this symmetric property so that we can treat the both vectors the same, say, oh, there's a bias term now for I, we'll also throw in a bias term for k. And now it's, yeah, so now we work out that we have this symmetric property between the two. So we're getting very, very close to the end. But an issue that they bring up is, okay, what about this log of 0? There's definitely a lot of zeros in this co-occurrence matrix. How do we deal with that? All right, so a very, very common solution that they say they could do is, all right, log 0 is an issue, we'll just add 1. Again, very common machine learning solution. But they have this other issue, and they want to solve them both at once. So we're treating all co-occurrences equally. We we know that most of them are 0. So there's a lot of zeros that are kind of messing with the whole thing. And the ones that coexist a lot are going to be really, really huge numbers that then are overvalued. So they want to not overvalue things and not undervalue things. So to fix that, they're going to use this weighting function. Yeah, here was the definition that they came up with. In the one that they present, they say like there are some variables that you can play with as kind of hyperparameters for the weighting function. This is the one that they said actually worked out for us. It just grows real fast, then stays at 1 forever. And yeah, it's going to solve the f of 0 equals 0 with the log. Or you want to define the f of 0 equals 0. F of x should be non-decreasing, and it should be small for large x. Yeah. All right. So finally, you can use this weighting function, and this is where they come up with the final model. So they cast the problem as a weighted least squares regression model, just like a very standard machine learning problem that they know how to solve for. You have the weighting function times this thing that we figured out a good function for earlier, squared. And basically, you want to minimize this function. You're going to sum over all I and j in your vocabulary, minimize the function, and whatever word vectors, context vectors, and bias terms give you the best result. Well, you're going to throw out those bias terms, they don't matter. And those word vectors are going to be your word embeddings at the end.
Yes, so you said a number of frames back that they wanted to take a linear approach. So is that saying that the transformation that takes you from your one hot encoded vector to the WI, is that a linear transformation? Is that what they're saying? Or
so here we don't have any one hot encodings.
So, but what we're learning is how to go from a word to its encoding, right, in a smaller dimensional space. Like the WI and the WJ
right.
are the encodings in the smaller dimensional space, but we don't know the best way to do that yet. Is that
so? In word to vec, you are, or at least like conceptually, you are taking this one hot vector and multiplying it by these by the hidden layer. Mm-hmm. Here, you're not doing that. You're essentially saying, all right, I have, for each of these are actually like 300 parameters that I'm going to be tuning in my machine learning model. So there's just like a bunch of parameters that you're gonna tweak until they look good. But there's not, I don't know if that makes sense. Like they're not grouped together in the same way. You're just very much training on this function directly.
Oh, so okay. So essentially, the matrix you start with is you have 10,000 words, and each word has 300 features.
Mm-hmm.
And so all of those 300 times 10,000, I should be able to do. All of those features, those are the trainable parameters. Yeah. Okay.
Well, and then also a bias.
And the bias for each.
Yeah, like one bias term for each, I guess. Yeah. Cool. And then the other like interesting thing that they do in the paper is because they've trained this these word embeddings and these context word embeddings that are essentially interchangeable. So they have a few different approaches. One is you can choose either or to be the one that you ultimately use as your embedding. I think what they do in the paper is they add them together. They're like, okay, I probably learned something good over here and learned something good over here. We're just going to add them together and like hopefully it's going to work. Sometimes I've seen that they average them. So yeah, that's it. All right, so evaluation, just real quick. So the complexity. So this algorithm, it needs to operate on all of the non-zero elements of this co-occurrence matrix. So at the worst case, it's the size of the vocabulary squared would be the complexity. But they find that in practice, it's closer to the size of your corpus, to the 0.8 power, which is better than the complexity of word to vec. So check, that objective is good. Ish. And yeah, the other thing they do is they evaluate on some word analogy, word similarity, and named entity recognition tasks. And they find that GloVe performs very well, tends to beat similarly sized models, which again is sometimes hard to compare because these models are trained in very different ways. Yeah, like similarly sized. Yeah, and then like my closing thoughts. So I think GloVe is kind of this protest against a lot of these deep learning methods of, all right, let's just throw a ton of data into this pool of parameters that we're just kind of, it's just like a bunch of wires all together. We don't know what's going to happen, but we know that the data will show us something at the end. They're saying, no, this is like, we know things about language. We can apply what we know to come up with something better. And they basically say, or I think that like the simple and understandable model would even be worth it for a performance hit. But in this case, it does pretty good. Yeah, that's that. Any questions?
Well, first let's thank Michael for his presentation. So I had one, which was about a lot of the math which flashed by at the end. So in TF-IDF models, you have analogous tweaks and tuning. They're everywhere, up to including that bias and that one of adding one to that. Lucene does that too.
Yeah.
To get away from the log of 0. And a lot of that is important for efficiency's sake. I mean, the thing is, these abstract models, if you were to actually implement these things as real one-hot vectors, giant bit vectors, I mean, there's no way you would do that. Yeah, so the thing is that the actual implementations of these, like the efficiency of the computer science is really important. So the thing is, I'm wondering how, and I'm not sure that you're going to be able to answer this, but my intuition here is that a lot of this math at the end is important in terms of providing an efficient implementation, but and that's actually a big part of how GloVe succeeds. And you know, if we were to dive into that and design a real implementation of that, that would be important.
Mm-hmm. But
what you're saying is actually that the spirit of the model is everything that in your presentation that preceded that. Now, is that accurate?
Yeah, so I think, especially with GloVe, so they describe in the part where they say how they train it, that, for example, they're running it on like a single machine in a single thread. And they're very clear about the fact that, you know, we could get this to train faster if we wanted to, but I don't think there's a real need. Right, even so they're processing this corpus at first and they're just calculating all the co-occurrences. Obviously you have a bunch of separate documents. This is a great place to do like a very distributed system, figure it out, merge it all together. But for the sake of what they're trying to do, it's not important because, you know, you train the model first and then you wind up using the word embeddings that you've used, that you've learned. And like this training of the embeddings is very separated from any say at Google where they're trying to use it on search. They've trained this model offline. Maybe they're also making some incremental improvements online, but like kind of the bulk of the computation happens before. And I think there is a lot of research around, you know, now they're starting to come out with these, I forget what they call the chips, the special machine learning chips. TLUs, tensor or something or other.
Oh yeah, TPU, yeah.
TPU, yeah, yeah. So they're also looking at how do we train these things more efficiently, separately. But it's just for these problems, it's that the training is the vast amount of the compute, and once it's actually deployed, it's a lot easier. Yeah. Thanks.
Make an observation. A lot of the math looks very similar to image processing.
Mm-hmm.
Have they looked into, or has anybody looked into the similarity of context, for example, in image processing and in information extraction, which is somewhat what we're doing here?
Yeah. So I think in image processing, like the most popular, again, like in the neural net architecture sense, have been convolutional neural nets, CNNs. and I believe I'm getting this right, but I might be wrong, that they have applied some CNNs to some of these language tasks, where for a long time I think they were focused on GANs, or maybe it's the opposite. Yes, they are very much working together or applying ideas from the fields across both.
I want to say they've done word2vec with documents and maybe images as well, so you could have a similar thing where you could, measure the similarity. They're arrays.
Pixels and analogous concept?
I mean, they both can be represented as like
Sure.
numbers, real numbers in a vector.
Three different.
Yeah.
A magnitude. But I guess what confuses me about this, and I asked this question earlier, and maybe someone, certainly Martin, could tell me. So I'll ask it to everybody. What is the meaning of representing these like arbitrary set of like magnitude or this has this gender component and it is a number between -1 and 1 perhaps, or however it's scaled, and then there's all these different components. Like, what is the utility of representing it as in this form of a vector, and how are these values in turn computed?
So the easiest way to talk about this is to talk about LSA, latent semantic analysis, which is, so you have, in a vector space model, you represent the complete corpus has n terms in it, and you represent every document as a sparse vector in n-dimensional space. And then what you're going to do is these things that are off in various places, you see that two of them are close together in n-dimensional space, then they're probably pretty similar. And you represent the query as being also something that's in n-dimensional space, and you say that the query is similar to the document.
That makes sense.
So then the thing is that one of the great problems, you want to do the old more like this query, and turns out that doesn't work very well with classic vector space search, like ITF, IDF search engines. So what you do instead is you create this, you train offline something which does what we call dimensionality reduction, where instead of going from an n-dimensional term space, you go to say 100 vectors.
Sure.
And this is what latent semantic
And those are
analysis
intelligently
does.
selected.
Yes, it's basically it's projecting it over and over and over
Sure,
again.
sure.
As the easiest way to think about this is looking at some three-dimensional thing and then projecting it down to a flat space. You're just doing it from millions of dimensions down to 100 dimensions instead. And then so the thing is that when you have an n-dimensional space, every one of those slots in the vector, every component, represents a single word. But when you actually do all that dimensionality reduction, what do those words, or what do the remaining vectors then represent? Well, it's something sort of like categories, or sort of like features. And then you can say, say that you've been training on something having to do with music favorites. This is the one that I used to work on, so I knew this one pretty well.
Okay.
So, and you have like artists, and you're trying to see who belongs to what. The 100 vectors might be something approximating genres at that point. So then you can say that this is what Michael was getting at, where he was saying you have this clustering effect, and you can say, well, this kind of looks like the country cluster, and this kind of looks like the hip hop cluster, et cetera, et cetera. So that's what I'm not sure that I've quite coherently answered your question there, but
No, you haven't, and you've added something really interesting to it. I guess it seems to me that some components of that vector are more important to the structure to determining whether two words are similar or dissimilar. Like some component of the vector, some piece that represents its gender or what have you, that could be more important to determining the similarity of two words than other components. And so, when you, I'll leave it at that.
I found it was helpful to think about like the vectors literally represent what the word means. Like it's like this is a vector and like it represents like like what the word means. Like it made me think back to like I was a philosophy undergrad, and in the philosophy of language, like one of the things like meaning like is defined as how a word is used. So what a word means is like that's the definition of what meaning is. And
Yeah.
Context is meaning.
yeah, exactly. And like here, it's like literally the representation of that just turned useful. Just like yes, like what queen means or what king means like has to do with the context that it appears in. And so like when you do all of this ML stuff, you actually get like a vector, and like maybe this touches on the knowledge representation points earlier, like, and that vector like that represents what the word means.
Yeah, I mean he explained on that a little bit earlier, that personhood or gender or all of these things that are the constituent magnitudes of the vector. I'm not sure how you call a vector in 4 or 5 or what the various components of it are, but I assume it's just